SmartGeo is here utilized for pre- and post-processing Modflow 2005, but only few packages are implemented, and they are listed here in the user guide file of the SmartGeo software. So we can go on with a second tutorial, and so we copy the Modflow example file in the example SmartGeo project examples directory in this new working directory. We open the Argus 1 interface, and the evaluation version is fine, where we open the Modflow example. SmartGeo is created for dealing contemporarily many scenarios for the same domain, characterized by different boundary conditions. In this case, we want to simulate the behavior of a confined aquifer where the wells are activated in different periods of time by representing different pumping tests. So, in the Argus 1 project, we need to define 4 different scenarios, and we need to assign to each scenario the number of stress periods and the number of observing times. This is the maximum number of observation times, and this value can be changed also inside the Argus 1 project. In the first scenario, the well 1 is pumping a constant rate, and in the remaining wells the hydraulic head is observed. In the second test, in the second scenario, the well 2 is pumping a constant rate, and in the remaining wells the hydraulic head is observed, and so on. So for each test, 4 layers are defined. In the layers called flow, BC, and the name of the test, we need to define the flow boundary conditions along lines or polylines. And in this example we don't have flow boundary conditions of this kind, but for instance we can draw a new element in this way, and we need to assign to each element the name of the element and the flow rate for each stress period. In the layers called head, BC, and the name of the test, we need to define the head boundary conditions along lines or polylines. In this case, we have 2 elements called BC1 and BC3, where we have to assign a constant head boundary condition, and in particular by double-clicking on the element we can look at the properties. So this element is called BC1, and 20 is the hydraulic head given at the beginning and at the end of the stress period. In the layer called wells and the name of the test, we need to define the active wells. In the first test, we have the well called well 1, which is pumping a constant pumping rate equal to -10 cubic meters per hour. So the properties to assign are the name, the stress type, in this case is equal to 1 because we are setting a rate and not a pressure, and this is a constant flow rate to assign at the beginning and at the end of the stress period. And in the layer called obs points and the name of the test, we need to define the observing points. For the first test, for instance, this point represents an observing point of hydraulic head, and we need to define the name of the point and the times and the observing values, and also the weight to assign to each observing value, but at this moment we don't use this value. So please note that for instance in the first test this well is called well 1 and is representing a pumping well, but in the second test the same well is inside the obs point layer, because in the second test the well called well 1 is observing the hydraulic heads. So it's really important that we don't call with the same name different wells representing different boreholes, and it's really important that we don't call with the same name different lines or polylines representing different boundary conditions. So for instance, inside the head BC layer, we need to call this line in a different way than this line. For generating the hydraulic conductivity field, we have three possibilities. We can use a constant value of hydraulic conductivity. We can obtain a heterogeneous field by kriging the measurements of hydraulic conductivity, or we can generate a specially correlated random field by using the software called hydrogen. In this tutorial, we choose the second option. So in the direct measurements layer, we defined two direct measurements of hydraulic conductivity, and the heterogeneous hydraulic conductivity field will be obtained by kriging these two measurements. When all the layers are filled out, we can run SmartGeo by clicking on pies, run SmartGeo. We need to choose the working directory, and we can start to fill out the SmartGeo parameters. We need to define the mean of the logarithm of the hydraulic conductivity, which in this case equal to minus 4.5. The variance of the logarithm of the hydraulic conductivity is equal to 0, because we are only using a simple kriging and we are not performing a random generation, so this is equal to 0. The logarithm of the specific storage is set equal to minus 8.21, and the integral scales along the x and y directions for the hydraulic conductivity field are equal to 5 meters and 5 meters. The kriging parameters are these, and we select the shape of the covariance function as exponential, and we need also to set the Modflow parameters, the initial head values, which are the same for all the scenarios and equal to 20 meters. We check this option because we want to save the hydraulic head simulated, and we set the stress periods parameters, the initial time, the final time of each stress period, the number of time steps, and the multiplication factor, and also the type of the simulation, which is transient. If we modify the settings in the first line, the first row, all the scenarios will be updated with the same values. Here we need to define the geometry of the aquifer, so the top elevation of the layer, which is equal to minus 10, and the bottom elevation of the single layer, which is minus 40. And here other Modflow parameters are defined. We need to save the settings in the working directory in order to reload the same values for future runs, and we can run Modflow. When the simulation stops, we can visualize the results by clicking on SPICE SmartGeo post-processing, and in the working directory we can find the generated hydraulic conductivity field and also the hydraulic head simulated for each scenario. So we select the first scenario, we can select the observing time, 4 hours for instance, and here in this layer we have the map of the hydraulic head simulated at time 4 hours during the first test. Okay, that's all. Thank you for attention. Bye.